Sprite and Fanta, that's pretty decent. Pretty decent. Okay, so we are starting today Unit 8. Unit 8. If I'm being honest, because I'm always honest, if I'm being honest this time,
The hardest.
this is usually what people think is the hardest unit.
Oh no!
You said there was only easy ones left.
No, I said the last two units, like kinetics was easy, equilibrium was easy. So, I always wonder if I should, I always wonder if I should like say that, because like, some people are like, this is fine. The good news is it's a continuation of what we were just doing.
Wait, so unit, are we having a unit 8 test or chapter 14 and a chapter 15 test?
Unit 8 test.
So we have to do the chapter 15 problems.
Yeah, why wouldn't you?
You said there too.
You want
No, chapter 14 and 15 are together.
to?
So unit 8 covers both of those chapters.
This is the chapter.
Yeah, that's why it's going to take at least 3 days to get through. So,
At the least.
at least 3, probably more. Probably more. So, we are going to throw it back in the beginning of this unit. We're going to throw it back to acids and bases. We have talked about acids and bases once before. Yes? Do you remember the pregnancy day?
Yeah.
All right? That's the last time that we talked about acids and bases. So, let's redefine it. Okay, let's start easy. Let's redefine to make sure that we know what they are. So, acids can be defined in terms of proton what? Transfer. I love how you guys are all throwing out random chemistry things you've learned this year. I love that. Were you thinking of photoelectron spectroscopy? I love that. Okay. Their strength are in terms of ionization, or what we've been talking about is dissociation. Do you remember talking about dissociation earlier this year? If something completely dissociates, it is a strong acid or base. Remember, so I brought no clean clothes? Sulfuric, iotic. Did we come up with something else?
Yeah. It was something else. It was something with like cat or something.
I know that it was something.
Okay, I don't remember what it was, but we had that. And how they can be sorted into acid, base. I don't know what happened to Nathan. I'm a little worried about him. Conjugate pairs.
I saw this morning.
Did he think that we were eating lunch or something?
He was walking the other way.
The wrong way?
Yeah.
Oh, well, we're not.
Or someone
gonna
planted
show
his
us.
stuff
Are
there
we?
so people think he's here.
No, I saw his face. I saw his face. So, there are two definitions of acids that you have to know. Imagine a test where I list out acids and you have to like say Bronsted-Lowry, or Arrhenius. Okay? Imagine that being on a test. So, in a Bronsted-Lowry definition, an I can't talk. An acid is a proton, or remember, a proton is just a hydrogen ion, right? Yes? It's just H plus, right? If hydrogen loses an electron, wow, I'm still trying to talk. It's just a proton. I don't. Ma me me mo moo. All right, I'm good. Warm up. Music warm up. Okay. Donor. I know. The magnet. From that point, that was the most coordinated. I can't even talk. That was the most coordinated thing that I've done today.
All weekend I've been
Yeah.
studying. So what is that thing?
Donor. Hydrogen ion, comma, H plus, donor. A base is a proton acceptor. So this is how we define them already. This is how we've talked about so far. In Arrhenius definition, we say that an acid is a substance that dissolves. An acid is a substance that dissolves in water to produce hydronium, which is H3O plus. Star, 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 star. Hydronium is really important. Hydronium ions. A base is a substance, not an absence, that dissolves in water to produce OH minus or hydroxide ions. So we've not heard of hydronium yet, but hydronium is super important when we're talking about acids and bases. So here is a chemical example. If I have HNO3, which is what? Nitric acid, AQ, plus H2O, which is a liquid, in equilibrium with H3O plus, which is AQ, plus NO3 minus, which is also AQ. Which one of these on the left is my acid? This is my acid on the left, which means that the water has to be my base. Because what do bases do? Bases want to do what with a proton? Except, what do acids want to do with a proton or an H? Give. So that means that H3O plus, we call that our conjugate acid. And NO3 minus is our conjugate base. So C is conjugate. Because it now works both ways. Because now H3O plus wants to do what with a hydrogen? It wants to, now can, donate it, correct? And what would OH want to, what would NO3 want to do with a hydrogen? Gain it. So whatever your acid is, its partner on the other side is going to be the opposite. Make sense? With the difference of a hydrogen. Cool? I went snow tubing on Saturday. It was ice. It was incredible. We started out, the four of us were connected, and then we went almost to the barrier, so then they wouldn't let four people go. By the end of the night, all the lanes were single rider only. And because two people went together, and then they went through the barrier into the trees.
Oh my god.
Yeah, it was wild. What? No, the barriers aren't they're not like solid. There's one space. They went in between the barriers into the trees. Yeah, which so you could put your boots down to break, but I was just full sending it every time.
Yeah. Why not?
Why not?
Was it you that went in?
I did not. Where's Nathan?
Okay, actually, it's kind of concerning, Colin.
Okay. So in this example, water acts as a base.
He got his lunch and he forgot.
You're right. There's probably a urinal that was ripped off a wall. It's flooded. He is currently like this as the water is filling up. I'm just saying. HNO3. All right. HNO3 acts as an acid by donating a hydrogen ion. The hydronium ion is a product. Many times, just the proton, or H plus, will be written instead of the whole hydronium ion. So instead of seeing H3O plus, we'll just write an H plus, because it's not doing much anyways. Hydroxonium, all right, is a barely used ion because they mean the same thing. So if I write H plus, that's called hydroxonium. It's the same thing. Don't worry about it. Example 2. Example numero dos. NH3, which is AQ, plus H2O, which is a liquid, is in equilibrium with NH4 AQ plus OH minus AQ. Why don't you guys label what's your acid, what's your base, what's your conjugate acid, and your conjugate base. Was there a flood? Are you okay?
It's a mess.
Okay.
I've never had that happen before.
What did you say? What?
He fell asleep on the toilet. I've never had that happen before. I said I wasn't there.
Did you just hide the microphone?
I did.
Why?
Glad you made it back.
You asked. I didn't.
That yellow
How do
paper.
you even do
Hey.
that? Like, what do you do?
He's tired. Okay. The yellow.
Why do you?
My ratio at the moment for, in the last 10 days, days that I've slept, or nights I've slept versus not slept, is 5 to 5.
Okay.
That's like a whole bottle.
What you've missed. The yellow paper is for the field trip. Your parents got to do something on Final Forms. The white paper are the notes we've taken so far. We have a lab Wednesday. Also, when are you going to take your test? Tomorrow morning?
Tomorrow morning I have sex.
Yeah, I don't know if this is any better or worse than
Sure. I'd like to go over the tests. Yeah. Go with that. Okay. All right. Here. Which one is our base?
NH3?
NH3.
Why?
What does a base do with a proton? Accepts it. So here, water this time is an acid. That's weird. That's weird. Why is that weird?
Water's never acid.
So, water here was a what? Water here is an so it could be both. We're going to talk about it. All right, you guys are getting ahead of me. We're getting ahead of me. So NH4, if this was my base, NH4 is my conjugate acid, and OH is my conjugate base. Because NH3 accepted a proton and became NH4, correct? H2O donated, correct? And H to NH3 becoming NH4 and being OH minus. Here, we okay with that? Yeah. Okay, here, water acts as an acid by donating, all right? By donating hydrogen ion. NH3 acts as a base by accepting a proton. OH minus is the other product of this reaction. So wait, this means that water can act as an acid or a base, which is very, very important. This is called, water is amphoteric. A-M-P-H-O-T-E-R-I-C. Water is amphoteric. It can be an acid or a base. Notice all the stars I just put there. All right, that's important. Yes?
Are there many other things that are esoteric?
No. There's not many. And I can't even think of one off the top of my head.
The only one we're going to use is water.
Just Google it. I'm honestly not sure. If there's probably some things that would be like, they'd be in that neutral range, all right? But water is specifically called amphoteric because it can be either. Cool? What did you Google? What did it say?
Your connection is not private.
Okay, great. All right, so acid-base conjugate pairs. We've kind of already been like leaning into this. So conjugate acid and base pairs are related by a difference of a what? By the difference of a hydrogen ion. So on either side of the equilibrium or equation, whatever you want to write there. If we look back to the last example and assume it proceeds in the forward, so we'll assume it's moving forward direction, then NH3 acts as a base by accepting a proton to form NH4. Have you guys ever been to the Buckeye Diner on 71? So it's like one exit south of Snow Trails. There's this little train car like up on a hill. Yeah, it's a little diner. We went there for dinner after tubing. I got the Mega Dog, which is a half-pound hot dog with a half-pound of coney sauce on top of it.
Wow.
What?
That's an absurd amount of sauce.
It's a lot. It was incredible.
How is it?
The burgers were incredible as well. I still don't feel quite normal after eating that. This is like day 3.
Was that on Fast Food Hill?
Fast Food Hill?
Yeah, Fast Food Hill.
I don't know. It's down. It's one exit south. It's by Der Dutchman. What?
Oh,
You'd have to go past. Yeah.
I didn't know that was a diner.
It's a train car, and inside the train car, there's like a bunch of tables.
That's really cute.
So you should try it. Will, did you Google amphoteric?
Yeah.
What did it say?
A bunch of like metal oxides.
Okay.
Oxide, aluminum.
Yeah.
Aluminum,
That makes me
hydroxide.
It's going to be things that are close to neutral. Okay. But water is the thing we have to know about.
Did you eat the whole half pound of sauce?
I did.
You did?
I ate the whole thing.
Our stomach is
As I said, I haven't felt quite normal since then.
literally steel. How large?
Huh? Do you want to see a picture?
Yes.
All right.
Yeah, I'm like confused.
Guys, I can't like describe like the size of it. Like, this is what it looked like. All right? Look at that. It was probably like this long. I picked that thing up. With cheese sticks. But I shared the cheese sticks with my daughters, okay?
It's just cheesy.
Like the top.
It was probably like this. It was crazy.
Wait, what is it called?
I don't know. It's called the Buckeye Diner. Called the Buckeye Diner. But I know you're not on your phone right now. Okay. Okay. Class change. Yeah.
Last change.
Okay. If that same reaction, so we're talking about these conjugate pairs, went backwards, then NH4 would act as an acid by donating. Guys, it was massive. And then my wife wanted me to try a bite of her burger, which I did. And that was amazing. It was a lot of food.
Yeah, I would be sick.
How?
I only ate one meal yesterday.
Yeah.
I'm only really planning on eating like mostly, I have just like a cucumber and like a clementine pack for lunch today.
Yeah, you ate
So I'm trying to recover
Some snacks.
slowly, yes. Yeah.
That's a combo.
I wanted a C lunch, double C. Yeah, C squared.
That's a recovery.
Squared.
What?
That's a recovery. Like, it's very-
What'd you-
Lunch.
Yeah,
only 2.
not CCC, just CC. Okay. This makes them an acid-base conjugate pair. This makes them an acid-base conjugate pair. How have we only got one page in and we're one period in?
Man, if only I knew.
So we just labeled those. So strengths of acids and bases. So let's list out our strong acids again. We have HCl, we have HI, we have HBr, we have H2SO4, we have HNO3, and HClO4. So I brought no clean clothes. But what did we came up with something different, I thought.
Yeah, no, we definitely did that.
I don't remember what it is either. But those are my strong acids. Everything else is a strong base, a weak acid. What were our strong bases? Alkali, metal, hydroxides. So sodium hydroxide, potassium hydroxide, lithium hydroxide. Those were our strong bases. Cool? Strengths of acids and bases. So a strong acid, we already know this is still review, completely does what? Dissociates. A strong acid completely dissociates. It's nice. Or undergoes complete ionization. Same. For example, a strong acid, let's look at HCl. And a strong base, B, in the following reactions go to completion or completely to the right-hand side to produce a large numbers of, that should not say or, of H3O plus and OH minus. So if I was going to write that down, it would look like this. HCl AQ plus H2O liquid is in equilibrium with H3O plus AQ plus Cl minus AQ. Right? Or, yes?
Is CL then considered the base?
This would be my conjugate base. That's my acid, that's my conjugate base. Because this could then accept a hydrogen.
Wait, does that say
Yeah,
H2O?
Liquid, yes.
What is water?
It's a liquid. Or I could write it like this. Base, so I could say base, any kind of base, plus H2O, liquid, would be in equilibrium with OH minus AQ plus BH plus. So it's going to be one of those two things, right? Yes?
Yes.
Okay, good. In the first reaction, lays. If the first reaction lays, in other words, is favored, right? Almost 100% to the right-hand side, then HCl is a very strong acid compared to H3O+, which is going to be the acid in the reverse. It is true that the conjugate base of HCl, which is Cl-, is a very weak base. This is true of all conjugate pairs. This is true of all conjugate pairs. So, if I have a strong component and a conjugate pair, will always be accompanied by an equally weak partner on the other side. So if I start out with a weak base on the left, its conjugate is going to be a strong acid on the right. You got it. So weak acids and bases, on the other hand, have very little ionization or dissociation. Same thing. So the equilibria of these lay heavily to the left-hand side, or the undissociated form. These don't want to break up. They don't want to break up. So how would this look? If I had a weak acid, HA, plus water, forget the states. Ionization, it does. Gives me H3O plus A minus, or B plus H2O gives me BH plus OH minus. I know it's repetitive, but we want to get this form over and over and over. But on these, what's this HA going to do? The HA is going to want to stick together on this side. Very little of it is going to go to the A minus. So would this have a large K or a small K? Small K. Have a small K. Whereas a strong acid would have a large K, because you're going to have a lot more products. So we can now think of K in terms of acids and bases. See where we're going with this? Okay. No, that's okay. Consider the 4 diagrams below in each case, where HA is an acid represented by 2 dots. H plus is the hydrogen ion represented by gray dot. And A minus is an anion and represented by gray dot. Okay. That's okay. And the water molecules are represented by white dot. It's okay, this is still going to work. Which diagram represents a concentrated but weak acid, and explain? So which diagram represents a concentrated but weak acid? What would you guys say? A, B, C, or D? Raise your hand if you think you would want to try. Concentrated but weak acid. He was out.
I think B.
Why? You're right. Yeah.
I don't know, it's either A or B, because they have like the paired ones.
Exactly. It had to be A or B, because that's where the acid was staying together, correct? But it said a concentrated but weak acid. So concentrated means there's going to be less what? Less water. So this one has less water. This one's mostly together. So that is B. Nice job, Derek. Well done.
100% yes.
Okay, well, let's see if you can keep going.
All right.
Number 2. Which diagram represents a relatively concentrated but strong acid?
So it'd probably be A.
But the A is so No, because it's strong acid, so it would be C.
It'd be C. Because what do strong acids do? They break up, right? So I know in this one it has to be C or D, but it says concentrated, so I need less what? Less water. Less water. So then assign relative strengths and concentrations to the 2 remaining. So A, how would you describe it? I would say a dilute, weak acid. And how would you describe D?
Strong acid, but it's also not concentrated.
A dilute, strong acid. So this is one of the misconceptions that people don't think about till this point in their chemistry journey. Till this point in your chemistry journey, you've done hydrochloric acid. You've used hydrochloric acid as a freshman, correct? Strong acid, right? You use hydrochloric acid as a junior or sophomore, depending on when you took it. Strong acid. Hydrochloric acid has a like molarity of 15, no matter what. unless you dilute it. It's still going to dissociate the same amount. It just depends how much water is with it. That's also why you put the water in first and you put the acid on second, if you're ever mixing chemicals. I always remember, do what you oughta, add acid to water. That's how I always remember it. Because what is that water doing to the proton on that acid? It's ripping it off. Yes. The water is ripping that proton off.
So why do you remember, what is the logic?
Great question. So if I put the acid in first, correct? And I pour that water on top, guess what's going to happen? It's going to fly straight up. If I have all the water here first, and I pour the acid on top, there's already hydrogens to accept it, right? So if you put that strong acid in the bottom, there's nothing there to accept. As soon as that water comes in, it's starting to rip, 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 rip. If you put the water in first, put the acid on top, there's hydrogens to accept as it dissociates. So there you go. Anytime you're mixing an acid, do what you oughta, add acid to water.
So you know your process.
I did. I have a aloe, thanks to Haley. Did Danny have any part of that? No, okay.
I carry this.
Okay, well, thank you. Thanks, Danny. I really appreciate it. Yeah. So you can have a dilute weak acid is what I'm saying. Cool? Flip it. Let's keep going. So here we go. Whenever I say note, these are just like, you guys know what I mean. This is just stuff I'm saying. I don't know how else to put it in like guided notes. So note, the concentration of H3O plus and OH minus are dependent on two factors. One is the strength of the acid or base. For example, the degree of ionization or dissociation. Could you see us like having to calculate that degree of ionization? Could you see that being a thing? Yeah. Almost like a percent ionization.
I like that.
Okay, we will. Or the amount of water present, aka the concentration of the solution. The concentration of the solution. So one of those things. Or both. This means it's entirely possible to have a dilute, this is what we were just talking about, but still strong acid, and to have a concentrated but weak acid that would have the same hydronium ion concentration and thus the same pH value. So here's what pH is. That's a pretty good transition.
Yeah. that
Just
was-
have to say. Speaking of pH, the pH scale is used to indicate the relative acidity or basicity. Isn't that a fun word? Basicity of an aqueous solution. How do we feel about the Super Bowl last night? The game was boring.
I like the
Commercials were above average.
The halftime
I liked
performance
it.
was bubbly.
I thought the halftime was cool.
Thank you. A lot of people are hating on it.
I'm hating on it.
I just like it.
I don't really like listen to like a lot of like rap, and that's fine. But I thought like the effects and like it was cool.
Serena Williams.
I did. But that that was a diss, right? Yeah,
It was the whole
it's crazy.
It was good. And then SZA.
Yeah.
I thought it'd be cooler if Drake came out and sang on stage and they like dissed on. I thought that was gonna happen.
That'd be wild. Okay, so here we go. Traditionally, these scales range from 0 to 14, and pHs less than 7 are considered what? Acids. While pHs greater than 7 are bases. And 7 is considered what? Neutral. Where are my lifeguards at?
Right here. I literally just said that.
So, you're going to now understand what you're actually doing when you're checking the pH. Also, we are going to see later how 7 isn't always neutral. Once again, we're breaking rules. All right? We're breaking rules. 7 isn't always neutral. So, when one is asked to take a pee, Look how I wrote that. Take a P. Just a P. You will now never forget what this means. If I tell you to take a P, you will now know that pH is equal to the negative log of the concentration of the hydronium ion. So when someone says take a P, they're really saying take the negative log. So that's, I know. So whenever it says take a P, take a negative log. Okay? That is what P means in pH, a negative log. What about POH? That's also a thing. Guess what that is? The negative log of the concentration of hydroxide. So there's pH and there's also POH. So the good thing is these calculations are not bad at all. Now, if you have a strong, these are base 10, right? So these are not bad. If you have a strong acid or base, dissociation is assumed to be 100%. Therefore, the concentration of H plus or OH minus can be determined directly from the stoichiometric, I'm not going to write that whole thing out, I'm just going to write stoic ratios in the balanced equation and the concentration of the acid or base. For example, sodium hydroxide and nitric acid are a strong base and acid respectively. This means that when they ionize, dissociation is complete. Dissociation is complete. So 0.01 molar solution of each will yield 0.01 molar of OH and H plus, which is the same thing as H3O plus, remember? Yes? The major species in a solution of a strong acid or base will always be H3O plus and OH minus. So let's write out that equation so you guys can see what that would look like. So I said that we've got NaOH, right? So I have NaOH, which is aqueous. Notice how I'm putting states more often now? Plus H2O, which is a liquid. Why do I keep writing liquid there? Why is that important?
It's a liquid.
It is a liquid, but why is that important for us?
Does it have to be a liquid state to dissolve?
What are we going to be doing? What kind of calculations are we going to be doing with these? Ice. This is not part of it, right? That's why I keep writing liquid. You're not water. We don't care about the water.
Water break.
It's the same thing. It's the same thing because it's just a hydrogen ion.
Or why is this the olive one?
I'll show you. When we get into ice, it'll make more sense. Okay. So NaOH plus H2O is going to be in equilibrium with what? That was a good hydration break. I appreciate that. It's lighting up really well. It's going to light up right now.
Every time you say that, it doesn't.
It's going to light up right now.
Right now.
Right now.
It's just shot.
Like right now.
I really thought it was a scam.
Yeah!
Kenny, did you see it?
Magnet.
Kenny didn't believe in it. You're laughing.
What's this going to give me?
H3O plus.
H3, well, really, NaOH is going to break up, right? Yes? Into OH plus Na plus H2O liquid. I'm trying to show you what's actually happening, okay? Because what does NaOH do? It completely dissociates. So if I start out with 0.01 molar of this, right? What's my molarity of OH going to be? 0.01 molar. Why? Because all of this OH minus went to all of that OH minus, right? Because it completely dissociated. This is what you want. All right, this is what you want. Let's do it the other way. If I had HNO3, there's not a lot of room, I'm sorry, plus H2O, that'd be in equilibrium with H3O plus NO3 minus.
Question.
There's also water floating around there. Yes,
So is it always gonna either have hydronium or hydrogen?
pretty much. Because if I want to take a P, I need a pH, I need hydronium. If I need a POH, I need hydroxide. So it needs to be one of those. So if I have 0.01 molar of HNO3, what's my molarity of H3O plus? 0.01. Guys, what is HNO3 really doing? Don't write this down. All right? HNO3, if I ignore the water, is really just breaking up into what? Do you see how this and this is the same thing? That's why. All right? This H plus and H3O plus is the same thing. Water's not part of it. The water's just there in order to make it happen. So all of this molarity goes to all of that molarity. Cool?
Yes.
Since we know the concentrations of OH minus and H3O plus, we can directly take a P. Or we could also use that at standard conditions, which is 298 Kelvin, 14, this is going to blow your mind, equals pH
Right there.
plus POH. Check that out. Does that make sense?
I like 7 plus 7.
Why 14?
Why 14?
Well, that's the.
That's your pH scale. That's the highest you can go on the pH scale.
H can only get up to 7. POH can only get down to 7, basically.
Yeah, but ours was like.
Added together, they have to equal 14. Don't set numbers here. Okay? This could be 1 and 13. Right? But you have to know added together, they are going to be 14. So if I said, what is the pH of the solution, or POH, this is how you will figure it out. pH equals the negative log of H plus. So if I'm doing it for this one up here, I would take the negative log of what?
Is it concentration of H plus or just H?
The concentration of H plus. Negative log of the concentration of H plus. So what was my concentration of H plus? H3O and H plus are the same thing.
I'm at 0.01.
Yes. So pH equals the negative log of 0.01 molar.
Yes, but he did. I got permission. I got the glare of.
Oh, I didn't know.
He's gonna get it on her process.
pH is 2.
Sorry guys, sorry.
pH is 2.
It's 2.
Do I need to calculate out POH? No, what's POH? It's 12. POH is 12 because 14 minus 2 is 12. Got it? So this is the kind of calculus we're going to start doing.
I already stop here for the rest of the chapter.
No, let's keep going. Because it's another K. Another K. Specifically, KW. KW is known as the ionic product of water. Pure water is essentially what? Covalent or ionic? That's what I'm asking for. Covalent or ionic? It's covalent. Pure water is covalent, but there's a small amount of self-ionization that happens. In the below example, we will write, and therefore, an equilibrium constant can be written. It's going to blow your mind. Equilibrium constant can be written. Are you guys ready to have your minds blown these last 5 minutes? H2O liquid plus H2O liquid. I know, this is wild.
Oh, wait. I already hate this.
It's going to give me H3O plus OH minus. Agreed? This is why water is amphoteric, because you can get both ions out of it. This kind of starts wrapping it up.
Okay, water.
So,
Wait, so if I put
Okay,
two
water, I
waters
see
together,
water.
wait,
so water, remember, if my water in here is going both ways, right?
So I'm drinking Vietnamese.
Technically, yes, but it's going both ways equally. All right? Going both ways equally.
So wait, technically there's OH
Water
in
break,
my water.
water
too,
break
you know?
for that.
There is, but it's an equal amount. So if I was going to write KW for this, what would KW be equal to? Still products over reactants. Concentration of H3O plus times the concentration of OH minus. Do I have any reactants?
You don't include.
No, because those are liquid-liquid, right?
Oh, so they get.
So KW is just concentration of H3O plus times concentration of OH minus. Yes.
Is this where like, you know how there's like water bound or pH bound is water? Is that like what this is?
Exactly what this is. Or if you have like, some people buy like alkaline water, right?
Yeah.
That's going to have a little more OH than H plus.
What are the benefits of that, or is it just?
It's kind of not, it just, it's not a, it's a pseudoscience. So like some people, well, it just depends. You're just essentially getting a little more acidic or a little more basic when you're drinking it. Your body's probably going to
I like my water.
synthesize either way.
For swimming, it's better to have it balanced because there's so much like chlorine in the pool.
Right.
Because then it's like balances.
You
out
got it.
Pure stuff.
So, as for any K, KW is depending on temperature. Let's finish this. We can do this. At 298 Kelvin, standard. That's not STP. What's STP? 273, right? So this is standard conditions. At 298 Kelvin, KW is equal to 1.0 times 10 to the negative what? 7th
Oh, because that's what, because it's neutral.
molar, right? Since pure water will have equal concentrations of H plus and OH minus under these conditions, we know that H3O times OH minus should equal 1 times 10 to the negative 14th, right? Because what's the negative log of 1 times 10 to the negative 14th? 14. And that means that H plus equals OH minus, which is 1.0 times 10 to the negative 7th. If I take a P, the negative log of H means the pH of pure water is what? 7. That's why.
Wow.
This means we can take a P of KW as well, which would be known as PKW, because we're going to start having PKWs, PKAs, PKBs, all right? So we're going to have P base, we're going to have P acids. That sounded weird saying that.
When you see pH, it's the negative.
The negative log, you got it. So PKW is going to equal what? 14, right? Which is POH plus pH. Putting all these K's together, KW equals 1 times 10 to the negative 14th, which equals KA times KB. Agreed? Yes? Or PKW equals 14, which equals PKA plus PKB. So that is just saying all of this stuff over in regular form and in log form.
So when you see the PKW, that's the negative log of KW?
Yes, PKW is the negative log of KW.
I honestly get this.
This is not bad.
Yeah, it's not bad.
And here's the thing. When I say this is the hardest stuff, I should probably just stop saying that because I teach this better than I did 5 years ago. So.